prove that the Euler function is a multiplicative function. Now proof, since phi1 is a result is trivially true if either of m is equal to 1 or n is equal to 1, thus we can suppose that m is greater than 1 or n is greater than 1, then phi mn is the number of the integers in the set curly bracket starts 0 1 2 so on m n minus 1 curly bracket close is equation 1, which are to prime to mn. The mn are integers in the set 1, and in view of the theorem division algorithm, we uniquely represented in the form of mq plus r, such that 0 is less than equal to q is less than equal to of n minus 1, and 0 is less than equal to r is less than equal to of m minus 1. Since we know that greatest common divisor of bracket starts a plus kb comma b is equal to greatest common divisor of a and b, where a, b and k are the integers. So we have greatest common divisor of bracket starts mq plus r comma m bracket close is equal to greatest common divisor of r and m. The greatest common divisor of bracket starts mq plus r comma m bracket close is equal to 1 if greatest common divisor of r and m is equal to 1. The definition of the phi m claims that there exist phi m values of r satisfying the condition that greatest common divisor of r and m is equal to 1. Let these phi m values of be denoted by r1 r2 so on r phi m. Now consider the n distinct integers x q is equal to mq plus r1 bracket starts q0 q1 q0 1 2 so on n minus 1 is equation 2, each of which is a prime to m. This claims that no of two of these have the same principal remainders with respect to n. For this, suppose that xq1 and xq2 bracket starts q1 does not equal to q2 bracket close have the same remainders, then n divides xq1 minus xq2. Now from 2 we have xq1 is equal to mq1 plus r1 is equation 3, and xq2 is equal to mq2 plus r1 equation 4. Subtracting 3 from 4, 3 and 4 we get xq1 minus xq2 is equal to m bracket starts q1 minus q2. Since n divides xq1 minus xq2, so n divides m bracket starts q1 minus q2. So n divides q1 minus q2, but 0 is less than q1 is less than equal to n minus 1 is less than n, which implies 0 is less than q1 is less than n, 0 and 0 is less than q2 is less than n. So q1 minus q2 is less than n, as we know that if a divides b and b is less than a, then b is 0, because so q1 is equal to q2, which leads to contradictions. Thus xq1 and xq2 have different principal remainders with respect to n. It follows in a view that the theorem of the division algorithm that n integers denoted by 2 can have a same order and be expressed in the form of nks plus s, where s is equal to 0, 1, 2, so on, n minus 1, where ks, k1 and so on, kn minus 1 are non-negative integers. Now greatest common divisor of a plus kb comma b is equal to greatest common divisor of a and b implies that greatest common divisor of nks plus s comma n is equal to 1 if greatest common divisor of s and n is equal to 1. Thus there exist phi n integers in the set 2 which are prime to n. Therefore there are phi n integers in the set 1 with the principal remainder r with respect to the m which are prime to m and n, and therefore prime to mn, because the greatest common divisor of r and m is equal to 1 and greatest common divisor of r and n is equal to 1. So greatest common divisor of r comma mn is equal to 1 by applying the same arguments to each of the other integers, r1 integers r2, r3 and r phi m in place of r1. It follows that there are r phi m and r phi n integers in the set 1 which are prime to m and n. Hence phi mn is equal to phi m into phi n.